Okay, thank you. Thank you for the introduction. Hey guys, thanks for making it to the last few sessions of the conference. I'm Hanyu from Alibaba Cloud, and today I'm more than happy to be here at Ray Summit to introduce Project Llumnix and report our experiences in optimizing LLM inference serving from a cluster scheduling perspective. Okay, let me begin with showing how LLMs are being served today from a cluster perspective. An LLM service is typically deployed as multiple instances of the model running inside a certain inference engine like vLLM with a request dispatcher at top, routing the incoming requests to the instances. For the inference engine layer, we have seen a lot of systems tailored for LLMs like vLLM or SGLang and many other systems. And these systems show superior performance inside a single instance. For the dispatcher, people are still using systems or scheduling policies that are inherited from the era of traditional DNNs, but not designed for LLMs. But the problem is LLMs are different and require new design philosophy for the scheduling layer. The first unique characteristic of LLMs is that workloads are heterogeneous. Because LLMs are universal models and can have diverse applications and therefore heterogeneous requests. First, requests can have different input and output lengths. Consider a simple intuitive example that you want to use an LLM to summarize an article or to write an article from a simple prompt or to polish an article you've just written. So these requests will have drastically different ranges of input and output lengths. Another aspect is latency SLOs. For example, interactive applications like chatbots or personal assistants would expect lower latencies than offline analysis tasks like summarize an article. A real product example is that OpenAI introduced a subscription plan called ChatGPT Plus, which promises lower latencies. The heterogeneity of requests becomes more challenging when combined with another characteristic, namely the unpredictable autoregressive execution. So during the autoregressive execution, the final output lengths are not known a priori, which also comes with GPU memory demands of KV caches that dynamically grow with the sequences. State-of-the-art systems adopt paged attention to enable dynamic memory allocation for KV caches and combine it with preemptive scheduling. Because if you cannot know the final KV cache size in the beginning, then you might have to preempt certain requests when you run out of the memory. These characteristics introduce a series of scheduling challenges that affect the performance and efficiency of online services. The first is the performance isolation. Preemptions are inevitable when you use dynamic memory allocation, and it can lead to poor tail latencies and SLO violations because the preempted requests will have to go through another round of queuing. Even without preemptions, requests in the batch also have performance interference to each other. So obviously, we need load balancing across instances to mitigate such issues. But the point is, load balancing via the one-shot dispatching could be suboptimal because the sequence lengths are not known in the beginning. That means we require continuous load balancing even after the requests are dispatched. Is that enough? No. Load balancing also means memory fragmentation across instances because we tend to spread the cluster's free memory space over multiple instances. Actually, this is a classic spreading versus packing trade-off in scheduling problems. Fragmentation can lead to worse queuing delays, especially for the long inputs, because the large space on one instance is needed for accommodating the KV cache of the whole prompt. To visualize this, we did an experiment with 4 instances using a spreading policy for request dispatching. We plot the memory demand of the head of line queuing request on each instance against the total memory space in the cluster. For most of the time span, the total memory space can satisfy the queuing requests on at least 3 instances, but they are still queuing because the free space is fragmented. This shows that beyond load balancing, we also need the ability to defragment the cluster's free memory space. A third challenge is to satisfy different latency SLOs of requests. Existing systems treat all requests equally, where the urgent requests could easily be interfered by normal ones. For example, they may experience excessive queuing delays or performance interference when co-located with normal requests. So we also need request priorities to systematically differentiate request SLOs. These challenges are fundamentally a result of the dynamic execution nature of LLMs. So we solve it by making request scheduling also dynamic. Llumnix is a system that features continuous rescheduling of LLM requests across multiple model instances. It is combined with the initial dispatching of requests and instance auto-scaling. We show that rescheduling is a powerful weapon in various scheduling scenarios. The first is rescheduling for continuous load balancing to reduce preemptions and interference, which is complementary to the dispatch time load balancing. To tame the trade-off between load balancing and fragmentation, Llumnix also reschedules requests away from an instance to create free space for defragmentation to reduce queuing delays. The third scenario is rescheduling requests away from high priority requests to further reduce performance interference and accelerate the execution of the high priority requests. Finally, Llumnix also reschedules requests away from an instance to create free space for, reschedule requests to saturate or drain out instances more quickly during auto-scaling. So the aim of Llumnix is to realize fully dynamic scheduling and make rescheduling the norm, not the exception in LLM serving. To this end, we need to accomplish a series of design goals. We need to maximize the efficiency of the rescheduling so that we can reschedule much more aggressively and more frequently. We also need high scalability of a cluster-level scheduler and a scheduling policy that maximizes the scheduling benefits of rescheduling for various scheduling goals. I'll first introduce the live migration mechanism in Llumnix. So the major concern with rescheduling is the KV cache states. You could either recompute or copy the KV cache to the new instance. But these approaches will introduce downtimes to the rescheduled requests for the recomputing or memory copying, and also performance overhead due to the redundant computation of recomputing. And more importantly, these downtimes and overheads will increase with sequence lengths. By contrast, Llumnix's live migration mechanism has near zero downtime and overhead by design. The inspiration is virtual machine live migration. When you want to migrate a VM, you keep the source VM online, during which you iteratively copy the dirty pages, namely the pages that got changed to the destination VM. When all the dirty pages got synced, then source VM stops, the migration is committed, and the new VM becomes online. Well, to apply this technique to LLM serving, we can liken the VMs to the requests and memory pages to the KV blocks. Now the question is, what are the dirty pages? So the key characteristic of LLM inference here is that the KV caches are append only. That means there are no dirty pages or dirty blocks, and there are only incremental blocks that are appended to the cache as the decoding proceeds. The live migration in Llumnix works in multiple stages, where we iteratively copy the incremental blocks generated in the last stage, and for the first stage, there are blocks generated before the migration, until we reach a stage that only produces the minimum number of new blocks, namely the stage n in the graph. So we suspend the request, copy the last blocks, and resume the request on a new instance. So this way, the migration downtime is only that of the final copying, which is near zero and constant to the sequence lengths. With live migration being the mechanism foundation, I'll next show you how Llumnix improved the scalability and scheduling benefits of migration. Continuous rescheduling across instances also implies higher scheduling pressure than in traditional schedulers, which could be a bottleneck if implemented in a centralized component. Llumnix uses a distributed scheduling architecture that employs a global scheduler for cross-instance scheduling decisions, while using a set of distributed schedulers named Llumnix co-located with the model instances to handle intra-instance scheduling. In this architecture, the global scheduler makes all the scheduling decisions only based on the memory loads of the instances reported by Llumnix. It does not need to track the status of every single running request, which further reduces its pressure. A key enabler of the global scheduler not caring about the specific running requests is our scheduling policy, which translates the various scheduling objectives to a simple instance load metric. We achieve this with an abstraction called the virtual usage. The intuition is that the various goals are all trying to manipulate the loads of the instances. You either balance them or you create more free space on certain instances. And they can actually be unified into load balancing because for creating free space, we can simply assume a virtual load on that instance. So this instance will be virtually overloaded, and the load balancing policy will be triggered to migrate some running requests to other instances. So Llumnix uses a load balancing policy based on virtual usages and defines the rules for setting virtual usages in different cases. For example, when we have a queuing request, Llumnix assumes a positive virtual usage of it, although the physical usage is actually zero, so that we can migrate other requests away, which in effect is defragmentation. And this approach also works for other scenarios. You can refer to our research paper published at OSDI 24 for the details. Llumnix was originally a research project, so we built a prototype implementation to evaluate the effectiveness of our idea. It was implemented as a scheduling layer on top of multiple instances of vLLM. We evaluate it on a cluster with 16 A10 GPUs using popular Llama models. We compare the serving performance of Llumnix with InFast, a system that implements explicit load balancing for dispatching. Llumnix achieves up to 2.2 times and 5.5 times gains for mean and P99 first token latencies, or TTFT, via defragmentation to reduce queuing delays. Llumnix also shows up to 1.3 times shorter P99 per token generation latencies, or TBT, by reducing preemptions with migration. On average, Llumnix reduces latency penalties caused by preemptions by 73% across these experiments. Due to the time limit, I'll refer you to our paper for other results like benchmarks of the migration efficiency, other traces, priorities, and auto-scaling. Okay, now that you've got the main idea of Llumnix, and in the rest of my talk, let's talk about implementation. Over the past few months, we have been working on a practical product-level implementation to bring this idea into production. Well, the key requirement in implementing Llumnix is to enable fine-grained interaction between the scheduler and the instances, and also interaction between each instance. The scheduler, it does not only need to dispatch requests, but it also needs other advanced interfaces from the engines like migrating requests or querying the instance loads as defined by our scheduling policy. For the instances, they also need the ability to talk to each other to enable migration. However, in existing serving infrastructure, it's difficult to realize our goal. The dispatcher does not have the advanced interfaces, and the instances are totally isolated and cannot communicate with each other. So conventional systems wisdom tells us if you cannot find a proper layer, then just add an interaction layer, right? So we've chosen to implement Llumnix as an interaction layer between the external dispatcher and the backend engines. Llumnix is compatible with external dispatchers because it exposes the same interfaces like the inference engines, namely API endpoints. And Llumnix is co-located with inference engines in the Ray cluster, and it manages components at Ray actors. So in this way, we can enable fine-grained communication between Llumnix and inference engines in a simple and efficient manner. Llumnix provides API endpoints via a component called the request proxy. In Llumnix, a request might execute on different instances in its life cycle, right? Because it could be migrated. But we need to ensure that even a request is migrated, its output tokens should be returned to users through the same API endpoint. So we bind each request to a proxy, no matter which instance the request is running on, and implement distributed token forwarding to send the generated tokens back to the proxy. The proxy provides a user interface that is very similar to existing systems like vLLM. So it is quite easy to migrate from an existing vLLM deployments to Llumnix, and you just need to change the path of the API server command. Llumnix is also compatible with different backend engines using a common abstraction in the Llumlet. In principle, the major assumption of Llumnix about the backends is continuous batching with dynamic memory allocation, like page attention, which has been the de facto standard of inference engines. So we have abstracted the common interfaces from the backend engines and implement these interfaces with a wrapper for each backend. So in this way, the Llumnet can integrate with different engines. And currently, Llumnix supports vLLM and Blade LLM, which is Alibaba's internal inference engine. Another important topic in implementing Llumnix is fault tolerance. Fault tolerance is non-trivial in our scenario. When the instances are all isolated from each other, then they are also naturally fault isolated. But in Llumnix, it is not the case because we introduce much more fine-grained communication between each component. So failure of one component or one instance, if not handled properly, could impact other components or even overall service availability. Let's first talk about scheduler failures. So currently, the scheduler is on the critical path of dispatching each request. So if the scheduler fails, Llumnix will temporarily enter a scheduler bypassing mode where each proxy directly dispatches each request to Llumnet, and the migration is disabled. So then the scheduled actor will be restarted by Ray automatically. When a request proxy fails, we will abort all the requests that have been associated with that proxy. We'll note that these requests could not only include those running in the Llumnet co-located with that proxy, but also those on other Llumnets because of migration. Similarly, when the Llumnet fails, we abort all the running requests on it. We also abort all the ongoing migrations on that Llumnet, namely the requests being migrated in or out on that Llumnet. Okay. One last topic I want to discuss is prefill decode disaggregation. I guess some of you guys might have already known this idea. Actually, many people are working on it. Well, basically, PD disaggregation is to run prefill and decode computation on separate instances. And you will have prefill instances and decode instances. This is mainly to eliminate potential interference between the two stages and also to utilize heterogeneous hardware because the two stages have different resource requirements. Well, today I'm not I'm not gonna discuss this idea itself, but I'd like to share another view to consider this idea. So how could we implement PD disaggregation? One could implement it in inference engines, right? You could label an instance as prefill or decode and execute different codes for different instance types. But we think that PD disaggregation is essentially a request scheduling policy, okay? So forget about the instance level concepts like P instances or D instances. Just think of how a request is scheduled on the PD disaggregation scheme. So a request first needs to be dispatched to a subset of instances, namely the so-called prefill instances. And then it needs to be migrated to another set of instances, namely the D instances, after one step of execution. That's it. So in Llumnix, we implement the PD disaggregation policy simply using a special dispatching rule and a special migration rule. And we call it the scheduling-defined PD disaggregation. What are the benefits? Well, first, this implementation reuses most of the system-level mechanisms of Llumnix that PD disaggregation also relies on. For example, the KV cache transfer, the token forwarding, because in PD disaggregation, you also need to forward the tokens from the D instances to the initial API endpoint. And also fault tolerance, because you need to handle P instances failures and D instance failures respectively. And all of these have been addressed by Llumnix with nearly no modifications needed. And another benefit is that it is non-intrusive to inference engines. The engines do not need to care about what type of instance it is, and it just needs to follow the instruction from Llumnix. And the last and the most important benefit is that PD disaggregation can seamlessly integrate with the scheduling capabilities that Llumnix already has. For example, for the initial dispatching, you need to choose one P instance. When migrating to the D instances, you also need to choose one D instance, right? And Llumnix already does this. And also, we can still use Llumnix routine migration between these D instances because the problem we mentioned before still exists in these D instances, and migration still works. So in Llumnix, the initial dispatching, the initial migration, and the routine migration are naturally combined and can complement each other. Well, we're still currently still actively working on this feature and developing and benchmarking it. Okay, to conclude, we believe that dynamic workloads need dynamic scheduling, and LLMs are no exception. We built Llumnix exactly following this principle. The design of Llumnix draws lessons from conventional systems wisdom, including definitions of classic scheduling goals in the new context of LLM serving, implementation of the rescheduling with the live migration mechanism, and fully continuous and dynamic rescheduling exploiting the migration. Combined, these techniques deliver better latencies and efficiency of LLM serving. Llumnix is open source and welcome to take a try. Okay, I'll still stop here and happy to take any questions.
Okay, thanks for the great talk. Yeah.
That was a great talk, thank you. I'm curious, when looking at the disaggregated serving via dispatch and migration, how does a prefill instance know the optimal decode instance to migrate to, or how to kind of approach that?
So the question is, when we want to migrate a request from a prefill instance to a decode instance, how do we choose the optimal D instance, right?
Yes.
Oh, okay, that's a good question. Actually, when you think of this, when you migrate a request from a prefill instance to a decode instance, it's actually the same as you choose a initial dispatching instance when you do not have the disaggregation of P and D, right? It's just another dispatching. So the logic is actually the same. When we choose a D instance, we normally choose the instance with the least memory load, namely with a load balancing policy. And we also have the same optimizations like defragmentation, like I said before, for the D instances. It's like when all the D instances, every D instance has insufficient memory to accommodate a request from a P instance, then we can trigger defragmentation. We will try to migrate some requests and make some room on one D instance and to accommodate a request from the P instance.
I see. And a related question, is there an assumption that instances have total access or unique access to like a device, like a GPU, and it's not shared with other instances? Or if it is shared, do you make decisions based on optimal location, like staying on the same device versus transferring devices versus transferring nodes, et cetera?
So the question is the assumption of the inference engines to the hardware or GPUs. Actually, that is it's like Llumnix is a scheduling system and built on top inference engines. And if the inference engines need to access all the GPUs, then we do not add more assumptions than the underlying inference engines. So, yeah.
Yeah, thanks a lot for the great talk. Kind of a related question. I got the impression for the live migration stuff, you do this sort of incremental transfer, right, where you can do the bulk while you're still generating decode tokens, and then just when you get to the last one, you
yes.
can then you minimize the sort of pause for a given sequence.
Yes.
You can't exploit that here, presumably, for the prefill disaggregation, because you've
yes.
got to transfer the whole thing.
Yes.
Do you start decoding on the prefill instance and transfer while you're doing that, or do you keep it exclusively prefill?
Yes, very good question. And actually, in the current stage, for migrating a request from a P to a D instance, we just pause it, and we do not apply the live migration technique. Yeah, and actually, we think that we can actually use live migration because PD disaggregation does not need to be that strict. For example, when you complete a prefill step on the instance, you can just do another few rounds of decoding if there are no incoming requests. So we are working on a policy that is smarter than that can automatically turn between the P and D modes for the same instance. We think that would be better than the strict disaggregation.
Okay, great, thanks. I had one other quick question. Do you take like SLOs into account with respect to your sort of maximum latency? So scheduler being aware of the batch size, like sometimes you might pile more requests onto a particular instance if they aren't latency sensitive, right? They only care about throughput. Does that make sense?
Sorry, I don't quite understand.
So you might have a mix of some requests might have a SLO where they need a minimum sort of ITL, and for that you might need to restrict the batch size. So how many decode requests you have in a batch on a particular instance, and then others might not. And so I was just wondering if the scheduler can take those kind of things into account.
In our current implementation, we provide an interface for setting the priority of each request. For example, if you mark a request as a high priority, we will try to limit the batch size or the total tokens of the running batch on that instance below an upper limit. that is one way to satisfy a certain level of SLO. And certainly, it can be improved.
Okay, thank you.
Thank you.
Yeah, I think we can have like 1 or 2 more questions, I think.
Hi, thank you. Thank you for the great insights. I had a question about scheduling affinity. So suppose you have a request which shares a prompt with a subsequent request whose prefill will already be done for the previous request. Does it have a routing affinity where it will send a subsequent request which shares a significant amount of prompt to the same prefill server so that it can reuse the KV cache?
Oh, so you mean multi-turn conversations, right?
Yeah.
Oh, I see. Yeah, we are now working on this. That means when you, because this project is about a multi-instance scheduling. So in a multi-instance setup, when you have enabled prompt sharing, then you need to consider this. Otherwise, the prompt sharing could be useless. You need to know where the prompt, the KV cache of the previous request is on which instance, right? We are actually working on this in both dispatching requests and also migrating requests. Yes, I think it must be an important feature. Yeah.
So right now it's stateless, right then?
I'm sorry?
It's stateless as in it doesn't consider any state from the previous request.
I mean, we are working on this. We are trying to consider the multi-turn conversations and their affinity in our scheduling policy. Does it answer your question? Oh, thank you.
Okay, our QA is kind of out of time, but after the talk, we can still like talk in person. Yeah, thanks for the great talk.
Oh, thank you, guys.